Okay, next question concerns a capacitor. You were given that it's a 10 square meter capacitor separated with two plates separated by, well, you have two 10 square meter plates separated by 0.003 meters. But it's instructive to work this out symbolically. Okay, so we're going to call the area A. The charge on the plate is Q, and before we had a charge of, I believe, 4 microcoulombs, but the charge is Q, the separation is delta X. So we've already done this problem with those numbers. Now the problem we're doing now is going to ask about the total energy to charge the capacitor, and we're going to then move to the energy per unit area of the resulting field. Well, okay. We first want to figure out maybe the capacitance of the capacitor, because we know that the energy is going to be Q squared over 2C. So if we can figure out the capacitance, we're pretty much already there. The capacitance is charge over voltage. So we know the charge, and from the area and so forth, we're going to be able to figure out the electric field as we did before and figure out what the voltage is. And then we divide that charge by the voltage, and we have the expression for the capacitor. We can get this expression in terms of these quantities, these symbols, and plug in the 10 square meters, the 3 millimeters, and the 4 microcoulombs if we wish. Okay, well, what's the electric field? We made the argument before that the charge density is, before it was 4 microcoulombs over 10 square meters. Now it's just Q over A. And the electric field then, we did a Gauss's law argument. Gaussian surface on one plate of the capacitor. Field exits the ends of the Gaussian surface, which could be a rectangular box or a cylinder, doesn't matter. We see that the area of the box, if the sides that penetrate the plate are perpendicular to the plate, the ends are going to have area equal to the area that we enclose here, so that the enclosed charge is just, let me back up here. Got to pause for a second and figure out a notation to use. I wanted to use A, capital A, for the area that's enclosed by this thing, but of course I've already used capital A for the area of the plates. So I'm going to use A box. And I'm not going to write it down, but that's the area enclosed by this box, but that's also the area of the ends of the box. And of course, this argument is familiar. We've made it a couple of classes ago. The enclosed charge, the flux, is 4 pi k Q enclosed, and you can verify that's 4 pi k times what? The density times the area of the box. Okay? And again, area of the box is the area enclosed by the box. But that's going to be Q over A, the density, times the area of the box. Now, the area through which the field escapes is double the area of the box. So area of the box is going to end up being divided out. So it doesn't really matter what the area of the box is. The electric field then is flux over area, where it's understood that the area is the area through which the field escapes the box. That's the area, the sum of the areas of the two ends, because it escapes through both ends. So that's going to be 4 pi k Q over A times area of the box divided by twice the area of the box, which equals 2 pi k times Q over A. So here's the electric field between the plates. So now we can depict the two plates from the end. We have, well, that's not the electric field of the two plates. This is the electric field due to a single plate. the total electric field is going to be double that. Remember that I tried to double that with a cylindrical capacitor, and didn't realize until I did the videos that I'd actually done that in class. And I think in class I actually discussed the implications of a Gaussian surface inside the cylinder. I just didn't seem to apply that. Okay, well, total energy, total electric field is 4 pi K times Q over A. Okay, so, and we get that. You've seen how we got that. We got that previously. The argument is the same when we do it symbolically. We have the same field. If this plate has a field emanating away from it, this plate has an equal but opposite field emanating toward it. In between the plates, those two fields reinforce one another. So we have an electric field in here. E equals 4 pi K Q over A. Now, separation of the plates is delta X. So that the energy per unit charge, or the voltage between the two plates, is going to be equal to E times delta X. We just imagine moving directly from one plate to another, perpendicular to the plates. It's going to have us parallel to the field, so that the voltage of the plates is just E delta X equals 4 pi K Q delta X over A. It follows that the capacitance, being the charge per volt, is going to be Q divided by 4 pi K Q delta X over A. Q's are going to divide out, A is going to end up here, and everything else down here. And that's going to equal A over 4 pi K delta X. Now, I had a note, and I didn't actually point it out in a previous screen, that 4 pi K, well, epsilon naught is 1 over 4 pi K, or K is 1 over 4 pi epsilon naught, but the 1 over 4 pi K gives an epsilon naught, so this is actually epsilon naught A over delta X, a fairly simple expression for the capacitance. So this epsilon naught thing gives you a kind of an elegant expression here. The advantage of K is it's an easy number to remember, and K is also nicer for a lot of calculations. But for capacitor, turns out epsilon naught is very handy, and we'll see fairly soon how much handier it can actually be.